Hi and welcome to MSc. In this video we're going to be looking at determining families of quadratics from their roots. So families of quadratics share a common element. For example, they'll have the same vertex, or it'll be a set of quadratics that will have the same a value, like that vertical dilation that'll do that vertical stretch or compression. Or specifically what we're going to look at here is having common roots, so common x-intercepts. So given the roots or x-intercepts, we can determine a whole family of quadratics, an infinite number of quadratics that will all have those same roots. And we can define that by substituting the roots into the factored form of the equation given down here for r and s, respectively. Let's look at an example of this. So we're going to find the family of quadratics that all have the roots of 2 plus or minus root 7. So what this means for us is we'll have two intercepts. We would have x1, and it would be 2 minus root 7, comma 0. And the other x-intercept would be 2 plus root 7, comma 0. So we can say one of these is r. r is equal to 2 minus root 7, let's say. And s then would be 2 plus root 7. Okay, so let's work through the equation that we'll have. We know that the factored form of the quadratic would be a, which is that vertical dilation piece, which we don't know in this case, because it's a whole family of quadratics, not one specific, and it's x minus r and x minus s. So when we sub this in, we're going to see some sign changes. Right? So we'll say a, and we'll have x, and I'll put them in brackets here, minus 2 minus root 7. Then we would have x minus, and subbing in for s, we would have 2 plus root 7. Okay, so let's get rid of these brackets, first of all. Those inner blue brackets. So we'll say this is being negative 2 plus root 7, and this would be x minus 2 minus root 7. Okay, so we have a bit of a sign flip there. Be careful when you're subbing in to this with the negatives that are there that will flip the sign. Now we're into the scenario where we have to distribute, and we're going to get one of those 9-term expressions coming out of this. Because, of course, this x has to multiply all 3 of these other terms. So let's start with that. We'll say equals a, we'll put brackets here, and I'll do this first expansion in blue. So this will give me x squared minus 2x minus root 7x, and that x is not under the root symbol. And then we'll have this distribution where we have the whole negative 2 distributing to the x, the negative 2, and the negative root 7. So this would be negative 2x. Negative 2 times negative 2 is positive 4, and negative 2 times negative root 7 would be positive 2 root 7. And then we have the last expansion, which would be this positive root 7 distributing to each of the other 3 terms. And this will give us our complete 9-term set here below. So this would be plus root 7x, negative 2 root 7, and negative 7 times root 7 is negative root 49. And you've probably seen this kind of trinomial by trinomial expansions in the past. We know that we're going to have some cancellation. We have a bit of a conjugate scenario where it's negative 2 plus root 7 and negative 2 minus root 7. So you probably have seen conjugates before, and we expect that we're going to get some simplification coming out of this. So let's see as we collect some like terms. There's no other squared term, so we'll drop it down. X term and x term. We're not going to try to add the root 7s because we can't add the 2 and the root 7 together very easily. So we'll say this is negative 4x, and that came from this negative 2x and this negative 2x. Then we'll notice that we have a negative root 7x, and over here I have a positive root 7x. And so those two will cancel with one another, which is great. Now we're on, we've already done this negative 2x. So now we're on to the 4. We'll just drop that down below. Plus 2 root 7 minus 2 root 7. So those will each cancel with each other, which is great. And we have negative root 49, which is negative of 7. Awesome. So this is a, and we can add those two last terms together to make negative 3. Awesome. So this is x squared minus 4x minus 3. And we can distribute that a, which is what we should do to put it in proper standard form, and say that our family of functions given by f of x is equal to a x squared minus 4ax minus 3a. And one of the things I find that students find challenging about this is a is supposed to be like this vertical dilation, the stretch or compression, and now we have it distributed all the way through. And we can see that negative 4 is not our b value if you compare it to standard form, right? ax squared plus bx plus c. But we have this a that's all the way through, and that can often throw some students. So just realize we have not defined what a is. A represents any value, and this thou represents the entire family of quadratics. If we click over to Desmos for a second, I already have this entered into Desmos. And if Desmos allows us to set this as a slider. And we can see that here we have a quadratic. We can see that we have roots at 2 plus root 7 and 2 minus root 7. And so what that means is actually we have our axis of symmetry is at 2. And it's root 7 this way and root 7 that way are my two intercepts. And if I play with a, we can see that this is the whole family. Now it only goes up to positive 10. But we have an entire family of quadratics here that all have the same roots, all have the same x-intercepts, right? And even over this small range, you can see that we have an infinite number of possibilities. This only goes up by a tenth. So this is what we mean by a family. This is an entire family of quadratics that's defined by this because the a can be any value we want, right? I can pick now a specific quadratic from this because, for example, this one is the only one that will go through that specific point, right? And so as I move this around, I could then say, okay, well, if I'm looking for a quadratic that has this specific vertex, well, then this would be the only quadratic that would do that. In fact, it's the only quadratic that goes through that point at all that's part of this family. So that's going to be the second part of our example. If we take this value, this quadratic, and we expand upon this example. So we're going to find the specific quadratic from this previous example that passes through this point. So I'll rewrite the quadratic that we previously found here. And I'll go back to this factored version of it where we didn't distribute the a. And whenever you have to find the specific one, that's always the one I would recommend that you go back to. Okay, and work from this. And the reason we do this is because a is already common factored out. And what we're saying here, okay, if it's going through this point, then we know that this is going to be my x value, and this will be my f at x value. So what we're really saying here is f at negative 3 equals negative 9. Okay, so we can say, okay, well, now we have negative 9 is equal to a, and now I'm going to sub in my negative 3. So I'll sub in my negative 3 squared minus 4 times negative 3 minus 3. So I have negative 9 equals a times 9 minus, oh, it's a positive because two negatives, so plus 12 minus 3. And this says negative 9 is equal to a, and this will be a positive 18. Right, so negative 9 is equal to 18a. And of course, we're trying to find this value of a that makes for the specific quadratic that passes through this point. So we'll divide both sides by 18 such that the 18s here will cancel, right, and just equal a value of 1. And so this gives us that a is equal to negative 1/2. Okay, so our quadratic here that specifically goes through this point is actually f at x is equal to negative 1/2 x squared minus 4x minus 3, and then we can distribute. Right? So we can say it's negative 1/2 x squared minus, well, this will be positive now, 2x, and this would again be positive 3/2. So the quadratic here that we found with this negative is given by this, where a is negative half. And we can tell that it's going to go through the point that we want because we said it goes through the point negative 3, 9. And we can just double check that that's the case. And there it is there on this specific quadratic. There. Okay? And so this is the only quadratic as part of the family that we found previous that goes through that point. Okay? So that's how families of quadratics work, specifically when we were looking at common roots or common x-intercepts. Thank you very much for listening. I hope you found this video helpful. If you have, please consider subscribing to the station and liking the video. And as always, thank you very much for listening and watching.